Once again, I welcome you all for today's lecture program. That topic is synergy-based human-machine interface. On behalf of IEI TLC, I formally welcome Professor Ramana Kumar Vinjamuri, Department of Medical Engineering, Biomedical Engineering Assistant Professor, Stephen Institute of Technology, USA. So now I request our chairman to give some formal presidential address.
Good evening. First of all, on behalf of the Institution of Engineers India, Tiruchirappalli Local Center, and the Institution of Engineers, Tamil Nadu State Center, and on my own behalf, I would like to welcome you all for attending this program. Every week on Tuesday, Tiruchirappalli Local Center used to organize the technical program for the benefit of fellow engineers associated under IEI TLC. This is to get to know the latest trend in technology of various engineering divisions from the experts or eminent personalities. So under this week, we have organized a wonderful lecture titled Synergy-based human-machine interfaces. So we have the wonderful speaker and very knowledgeable in this area, Professor Ramana Kumar Vinjamuri, Harvey N. Davis Distinguished Assistant Professor, Department of Biomedical Engineering, Dimensionality Institute of Technology, USA. Thank you, Professor Ramana, for gracefully accepting our invitation and sparing your valuable time. Really appreciate your commitment since you have started your lecture at 8:45 a.m. and for us it is evening 6:15. Thank you once again and welcome you all for attending this program. Over to Engineer Anand.
Thank you, sir. Let me give introduction about our today's speaker, Ramana Vinjamuri. Ramana Vinjamuri received his PhD in electrical engineering in 2008, specialized in dimensionality, reduction and control and coordination of human hand from the University of Pittsburgh. He worked as a postdoctoral research associate from 2008 to 2012 in the field of brain-machine interfaces in the School of Medicine, University of Pittsburgh, where he received Mary E. Swartz Merit Fellowship in 2020. He worked as a research assistant professor in the Department of Biomedical Engineering at the Johns Hopkins University from 2012 to 2013. He is currently an assistant professor in the Department of Biomedical Engineering at the Stevens Institute of Technology from 2013 to present. In 2018, he received Harvey and Davis Distinguished Teaching Award for Excellence in Graduate and Undergraduate Teaching. He received NSF Career Award in 2019. He received NFS IUC RC Center Planning Grant in 2020. His other notable research awards are from USISTEF and New Jersey Health Foundation. He also holds the secondary appointment as adjunct assistant professor at Indian Institute of Technology, Hyderabad, India. With this introduction, I request our today's speaker to take over the session. Thank you.
First of all, thank you all so much for inviting me. And it feels like I was just mentioning that it feels like I'm actually sitting in your house and presenting this research to you all. We are all caught up in these unprecedented COVID-19 times. I think we are all equally stressed all over the world, but thanks to technology platforms like Zoom, now probably GeoMeet or Google Meetups, that we can hang out and we can talk about research. We can share ideas, we can share knowledge. This is a great opportunity for me to be with all of you. I think Dr. Karthik and Dr. Shivakumaran and myself, we were planning that I actually come there physically in the month of August. But because of COVID, we are unable to do that. So I'm very, very happy that at least remotely, I'm able to be with you all and present my research. Thank you all for the kind introduction, and thank you so much for having me. So I'll turn my camera off for the presentation time, but I'll open it again during the question hour. So I'll just start sharing my slides now.
You can switch on your camera also.
Oh, okay. I just don't want to look away from the camera when I'm presenting.
Okay, no problem. Only you can see the screen and then you will.
Right. Okay. Okay. Sounds good. All right. So once again, thank you so much for having me here. So today I'll be talking about synergy-based human-machine interfaces. This is a very, very interdisciplinary research that overlaps signal processing, electrical engineering, machine learning, biomedical engineering, neural networks, deep learning. All of these fields put together is my research. It is very, very interdisciplinary. So let me jump right into it. So here is brief contents that I'm going to go through. So I'll start with the introduction, and then I'll talk about dimensionality reduction in control of human hand movements. Then I'll talk about neural representation, that is brain representations of synergy-based hand movements. And then some of the applications of these synergy-based hand movements. And then some future research, and then I'll close with acknowledgements. If you have questions, you can start typing them in the chat window, but I'll get to them towards the end of the talk. So my my research is motivated by these two questions: how human brain, an intelligent controller like human brain, controls a versatile robot like human hand while performing simple to complex movements. How is this brain able to do that? That is one of the first questions that I have, is how this human brain, which is a very, very intelligent controller, as we all know, is controlling a very, very complex robot that is human hand. How is it able to do that? That's one of the first questions that fascinates me. And the second question is how human hand, which is probably the best robot sensory motor device that is available in the world, in the nature, how does that feed back to the human brain, which is like a multi-input, multi-output parallel processing system? How does it do that? So these are the two questions that motivate my research. And for these two questions, I take two approaches. And the first one is a top-down approach, where we are recording brain signals using, say, for example, electroencephalography or EEG, or say, for example, I'm recording muscles. And then at the same time, I'm also recording human hand movements. So that is a top-down approach where I'm looking at the top-level neural signals and seeing what are the human hand movements and what are the corresponding neural representations. Now, the second approach is bottom-up approach, where I asked individuals to do a lot of hand movements, and I look at those hand movements by recording the hand movements. This is called a cyber glove. It is a data glove that can record hand movements. So after you record these hand movements, you start looking at the patterns and see if you can dimensionally reduce these hand movements and see if that can inform neural mechanisms or brain control mechanisms. So now, why are we bothered about these two approaches is, again, it comes down to what are the applications of this research? Where are we going to apply this research? So the first application is motor control. Can we improve impaired control in individuals with motor disabilities? So for example, if someone has paralysis due to stroke or spinal cord injury, can we help them using these technologies? Can we augment motor control in individuals with needs? Say, for example, soldiers. So if they have to put heavy weights on them and carry heavy weights on them, can we help these individuals with these technologies? And the second application, major application, is motor learning. Can we improve neuromotor rehabilitation? Can we improve rehabilitation, right? And rehabilitation is the process where somebody has to go through physical therapy to regain their lost movement. So also we have a very finite time to regain these hand movements or limb movements. We have very finite time. So in that finite time, is there any way that we can speed up this process? Can we speed up this process of rehabilitation? So these are the two big applications that we're worried about. So for these two applications and for these two questions, there seemed to be one possible answer, and that is synergies. And what this synergies means is working together. And Bernstein in 1967, he proposed this as a very high level programming principle. And what these synergies are, they are like building blocks of movement. So you can call them like Legos of movement. So just like you put letters together and you form words, and words together you form sentences, and sentence together you form language, right? So just like that, if you put these synergies together, you get sub-movements. If you put these sub-movements together, you get a movement. And if you put these movements together, you get a total movement behavior. So these synergies, just like letters are shared among a lot of words, just like that, these synergies are shared among several movements. So say, for example, you're doing a hand grasp, or you're doing a hand pinch, or if you're doing, if you're grasping a pen, or if you're grasping a ball. If you look at the pattern of movements that you're doing with your hand, there are a lot of shared patterns across these movements. So I'm really interested in these shared movement patterns, and those we call them as synergies. So what we understand is that from several movements, we can get these synergies. We can decompose these synergies. And once we have these synergies, we can compose them and we can get a lot of movements. And just like you can again use the analogy of putting together letters to form different words, or putting together like primary colors to form different colors, right? So there are several studies that demonstrated synergies in hand movements. So I'm going to give you one example here. So this is a very important slide. If you understand this, you will easily understand the rest of the talk. So here we have three synergies: synergy 1, synergy 2, synergy 3. The x-axis is time and y-axis is joints. So joints of the fingers or hand. Okay. So here we have three synergies: synergy 1, 2, and 3. Now these three synergies, they are combining at different times with different coefficients at different times, and they are giving rise to this movement profile. Okay, so if you see the synergy 1, 2, 3, by using a weighted linear combination of time shifts, you get this movement profile. So by changing the weights and by changing the times, you can get a lot of movements with the same three synergies. So this is a very important formulation that you can achieve any movement using these three synergies. The only difference is that you're going to be using them in different time shifts and different weights. And so this can be implemented as this equation shows. It's a very simple equation. It's a weighted linear combination. It's just a simple linear summation, but it's a weighted summation of time shifted synergies. So that you can treat these as matrices with rows are the joints and columns are the time samples, and what we're representing here is angular velocities of joints. Okay, so during my studies, I saw that this simple summation may be too simple to represent our complex hand movements. So I added one more summation just to make sure that we can reuse these synergies as many times as we want. Okay, so that's how you get an extra summation here. All right, so this is one of the important slides that you need to pay attention to. Okay, so once we know that this is how you can use these synergies and reconstruct movements using angular velocities. Now I'll give you an example. This is a very, very interesting example where I use this framework in a brain-machine interface. Okay, and so here is that demonstration. This is a very, very busy slide, looks like, right? So I'll explain to you what this means. So from the brain, I'm taking two signals and I'm controlling these two synergies. And by combining these with different weights and different time shifts, I can reconstruct a lot of hand movements. Okay, so we demonstrated this in an epilepsy monitoring unit in University of Pittsburgh Medical Center. So what we did was we took the brain signals from an individual. One electrode was in the motor region of the brain, and the other electrode was in the speech region of the brain. And we took those two signals, all right, and we were controlling two synergies. One was a grasp synergy, and the other was a pinch synergy. And so by using these two electrodes and by modulating the brain signal, we were able to control a virtual hand to either grasp a ball or pinch a pen. Okay, so we are using, essentially, we're using two signals to control 10-dimensional virtual hand. Okay, so we're using only 2-dimensional control signal, but we are controlling 10-dimensional virtual hand. So how are we able to do that? In between is the synergies framework that takes care of increased dimensionality. So this is the importance of this, this work, is that this can enable us to control higher dimensions using lower dimensional control signals. So this is a big advantage in brain-machine interfaces. So, so I'm not sure how many of you have neuroscience or neural engineering background, and I'm seeing that the last week's topic was on artificial intelligence applications, right? So this is somewhat similar to that, but this is also a little bit different. Okay, so so this is a general structure of how there is primary motor cortex, that is in the brain. There is primary motor cortex and other motor areas that talk to thalamus, to brainstem, and then spinal cord, and generate what is called synergy-based movement. Okay, and through this network, they interact with two important brain regions. One is basal ganglia, and the other is cerebellum. Okay, so basal ganglia and cerebellum. So if you look at this, this brain structure, we can go back to my equation. So by using primary motor cortex, thalamus, and basal ganglia loops, you can actually control the weights. You can actually extract the weights of these synergies, all right? And by using primary motor cortex, thalamus, and cerebellum loops, we can actually structure these synergies. So this is a hypothetical model where I'm saying that by using these three important brain regions, primary motor cortex, basal ganglia, and cerebellum, we can actually implement this equation in the motor cortex and see if this can help us in brain-machine interfaces. Okay, so so this basal ganglia, thalamus, and primary motor cortex interactions, this can be implemented with a spiking neural network. And primary motor cortex, thalamus, and cerebellum interactions, these can be implemented with recurrent neural network. So as you can see, I'm using a lot of artificial intelligence and deep learning and neural networks, but the application is biomedical. The application is to control brain-machine interface. Okay, so So with this model, I'm going to jump into the next part of my talk, that is dimensionality reduction in control of hand movements. So first, I'm looking at hand movements, and I'm trying to see if by looking at the hand movements, if this can inform me about brain. Let's see if we can do that. So this is the first part into the serious topics. So let's see the dimensionality reduction in control of hand movements. So the first part is that we get a lot of hand movements. We record all these hand movements by, these are healthy subjects. They're wearing this cyber glove or an instrumented data glove. And these subjects are grasping these objects, all right? And they're grasping a lot of these objects, and we're recording activities of daily living and what are called instrumented activities of daily living, where these hands are interacting with so many of these devices. And as you can see, this is the same hand that will perform simple movements like holding a pen or grasping a ball. And this is the same hand that will also do complex typing and playing a guitar, playing piano, for example. So it's the same hand that you do for simple and complex movements. So we record all types of hand movements, okay? And then we use what is called principal component analysis, and we dimensionally reduce these hand movements, and we see if we can get some building blocks out of these hundreds of hand movements. So if you look at these hand movements, they look like this. So this is the first synergy, where you see that it is completely closing the hand. And if you look at fifth synergy, you can see that it is trying to do a pinch with two fingers, thumb and index finger. It is doing like a pinch. And if you look at synergy 4, you'll see that it is trying to hold a cylinder with its hand, okay? So when we look at large set of hand movements and we get these dimensionally reduced to a few, 1 or 2 movement primitives, then they start looking like this. And now once we have these hand movements, now how do you select them, right? That's a big question. Now, how do you select them? And you can do that selection by using what is called L1 norm minimization. So you can use convex optimization to select these synergies. Now, let me break it down for you. So let's say this is the movement that you want to reconstruct. Okay, so I realign it in a vector form, all right? And then here is a matrix that is full of my synergies, okay? All right, and this is a second synergy. And then here are my weights or coefficients, that is the CIK, right? And so I express this equation in a matrix form, right? So here is y is equal to ax. This is the equation that I'm trying to solve. And I know what are the synergies, right? And I know what are the movements that are to be reconstructed. I don't know this x, that is the coefficients. So now this is the equation that I'm trying to solve. I want to see if I can get a very, very sparse selection. So I want to use only a few coefficients. I don't want to use all these coefficients. And the reason I'm doing this again is to replicate human brain, which is a very, very intelligent, smart controller. So if it is a very, very smart controller, it will pick and choose. Am I still there? Can you guys hear me?
Yes, sir.
Okay.
Yes, Professor.
Yes,
Okay,
Professor.
thank you.
Yes.
Okay, thank you. Something disappeared from my controls, so I'm just making sure. Okay, I'll continue. So I'm trying to see if I can get to solve this equation, y is equal to ax. And the way I'm going to solve it is to minimize this reconstruction error. So I want to make sure that this left-hand side of the equation and right-hand side of the equation both are as close as possible. And at the same time, I want to use as many sparse coefficients as possible. So that's what I'm trying to do, is that with y is equal to ax, all right? And then we realize that, so here is the original grasp, and here is the reconstruction. As you can see, by using this mathematical framework, I reconstructed the recorded movement, and the movements are very, very close, right? So, so from here on, so as you can see, I used this very simple linear dimensionality reduction method called PCA, right? And this is a very, very simple method that uses variance, all right? So we tried, because the hand movements are very, very complex, we tried to use other types of dimensionality reduction methods. And so that work was done by my first PhD student, Rajeshri Patel. And so we used a lot of nonlinear dimensionality reduction methods, and we compared which one gives us the least reconstruction error. And as you can see in the slides, still, even when compared to nonlinear dimensionality reduction methods, we were seeing that PCA, principal component analysis method, which is a linear method, was giving us the best results. And so we tried two types of different postures, normal postures and sign language postures. And I'm sure there is Indian sign language as well, but here we tried American sign language postures. And in both the tasks, we were seeing that principal component analysis apparently found the best synergies. We tried nonlinear methods, but we were seeing that they were not giving that good of synergies. And even within nonlinear methods, we were seeing that global nonlinear methods were much better than local nonlinear methods, okay? And so now that leads me to the second or the third part of my talk. Now we saw how by looking at the hand movements that can inform us about complex brain control mechanisms. Now what we want to see is, if we are looking at the brain signals, can they inform us about hand movements? So that's the next step we want to see, okay? So, these synergy-based hand movements have been decoded using the brain signals. You know, I'm not the first one to do this. This research has been done previously by several other researchers. In 2006, using transcranial magnetic stimulation, these scientists, Gentner and Klassen, they saw that these synergies are actually represented in the human brain. And we did this study in 2014, where we were looking at neural representations of synergies in electrocorticography. Electrocorticography is invasive EEG. And there was another professor, Contreras Vidal, we call him Pepe, and he did this research where he decoded 3 hand synergies using EEG signals. And there's also other research that was done by Adamovich in New Jersey Institute of Technology. They decoded muscle synergies using transcranial magnetic stimulation. And there's also a lot of fMRI and MRI studies that coded synergy-based motor control. And a lot of these researches, they all are hinting at one particular conclusion, that that you can represent or actually you can find neural representations of these synergy-based hand movements in the brain. So we were also encouraged by their studies, and so we thought we will also try to find these brain regions that are responsible for synergy-based representations using electroencephalography or EEG. But because of the low spatial resolution of EEG, it is very difficult to pinpoint brain regions that are responsible for synergy-based representations. So we took an indirect approach, and this is what we did. And I'll show you in just a little bit here. And this work was done by my 2 PhD students, Rajeshri Patel and Ding-Yi Pei. So here we took a little bit indirect approach. So we measured the hand kinematics, and just like you saw the pictures in the second part, we got the synergy weights, that is C, and we also simultaneously recorded the brain signals, and we got the neural features. And from here on, just like any machine learning exercise you do, we split up the data into training data and testing data. And using training data, by using multivariate linear regression, we developed our model, and we got these linear coefficients beta. And then with testing data, we predicted what will be C2 given X2. Okay, and with all this, I'll show you some results that you can appreciate. The weights of these kinematic synergies in a movement reconstruction, they're very, very strongly correlated to EEG features. And these EEG features we extracted are in a frequency range 1 to 45 hertz. And this is a normal motor frequency range we see in the brain. And we were getting up to 90% accuracy. So here, I want to point you to these reconstructions. So there are 3 waveforms overlapping each other. One is the recorded waveform, and another is synergy-based reconstruction. And the third one is using brain signals. If we were to reconstruct, what would that reconstruction look like? Now, as you can see, they're very, very closely overlapping, and we were able to get 90% accuracy in these reconstructions. And we were very, very happy with these results. Okay, so finally, by using all these results, what can we do with these results, right? So I'm going to give you 2 applications by using these 2 approaches, top down and bottom up. I'm going to give you 2 applications. So the first one is hand exoskeleton with embedded synergies, and we call this as HEXOES, hand exoskeleton with embedded synergies. So this is a 10 degree of freedom exoskeleton. So exoskeleton is basically a skeleton that you put on top of your hand, right? It's an exoskeleton. It's an outward skeleton, right? And it is made of 10 motors, and so it's 10 degrees of freedom. But it's a soft exoskeleton. It's a soft glove type. And the synergies are embedded in a microcontroller that controls this, right? And there are a lot of sensors built into these fingers that track hand movements. And so this type of exoskeleton with embedded synergies has many, many advantages over mechanically implemented synergies. And the difference is that these are soft synergies. You can change them. You can change them easily by changing a software program. You don't have to change the motors. And before I forget, this work was done by Marty Burns, my second PhD student. So these are functional and anatomical synergies. There are 2 types of synergies. There are functional synergies and there are anatomical synergies. You can actually program them directly into this microcontroller that will in turn control this exoskeleton. So there are a lot of advantages of these soft exoskeletons over rigid exoskeletons. This glove weighs only 250 grams. Your average human hand weighs about 500 grams. Okay, so we are not adding much weight. And the actuator and motor assembly is about 2 kgs, but this sits on a pouch or on a bag or on a table. So this is not adding extra weight to you. So we are trying to use what I spoke to you in the first 3 parts, and we're trying to impose a low dimensional control method over a very high dimensional system. The low dimensional control is the control signals that you get from the brain or muscles, and high dimensional control system is this high dimensional robot, okay? And this research is very, very interesting, and this got funded by New Jersey Health Foundation and National Science Foundation. Okay, so let me show you a video where we are using these technologies to control a hand exoskeleton. Okay, here is a video. It's about 3 minutes, I think. Let me see. Are you guys able to see this video? Can you see the slides moving? Can you see the video?
No, we are seeing only a slide.
You're not seeing anything moving? Any?
No.
Do you see the? Now it is moving? Okay. Okay, good. Thank you.
And now it is moving.
Okay, thank you so much. So this is the hand exoskeleton that we're trying to control. And we're using, here we are using functional synergies. So that is either we move the thumb or we move the index finger or we move the 3 fingers at a time. So this you can think of like XYZ, okay? All right, so by controlling this, so by using the muscle signals, and this is our lab, by using the muscle signals, we're trying to control the movements, that the 3 demonstrating movements, either the thumb or the 3 movements or a combination of these movements. So here we are training individual movements, and now here he's doing combined movements. Now he's trying to pick up objects using these movements. So here he's picking up a water bottle, which is a little bit heavier than the eraser that he was picking up in the previous task. So he's using the muscles on the other hand to control the exoskeleton on the right hand. We also tried some heavier objects. This was about 2 kgs. So he's able to lift that with the grasp power that is within the exoskeleton. So by using the muscle signals, he's able to either flex the hand to grasp something or to relax the muscles to open it. Okay. So let me go back. So this was one application, and the another application is in motor learning. So if you want to learn any new motor task, any task, if you want to learn, you have to repeat it, right? This is traditional learning, and this is how rehabilitation is based on, right? But the research shows that experience-based learning is better than exposure-based learning. So instead of repeating 10 movements, if you were to repeat, say for example, synergies, you might be able to get better at the task quickly and in a shorter time and more efficiently. So this is our hypothesis again. And this work was done by my other 2 PhD students, Rajashri Patel and Dingy Pei. So so let me give a very, very interesting application here. Is if I were to teach you how to play a piano in 1 or 2 weeks, right? Would you be interested in that, right? So everybody will be interested in that because everybody wants to learn piano in 2 weeks, right? So, but how do you learn a complex motor task in a shorter time? How do you do that? So we devised a new task here. So here is our task where, you know, you have to do button pressing, okay? So it is like a typing, but it is not a regular keyboard typing, but it is like a button pressing task, okay? So we will show you what buttons you need to press, and you need to make a certain posture to get to push the buttons, okay? So it is somewhat complex. It is not so difficult, but it is somewhat complex task. So what we did was we split the subjects into 3 groups. One group was trained on these movements itself. The second group, we trained on synergies that were derived from these movements. And the third group was a control group which received no training. And so we wanted to compare across these 3 groups to see who will do better if we give them new movements, okay? So that's the task here. And we saw that if you test on similar movements, all 3 groups were performing in a same way. But if you test on new movements, then synergy-based training is far better than repetition-based training. So what it means is, if I were to train you on, let's say 12 alphabets instead of 26 alphabets, if I train you on 12 alphabets, then you can perform much better in doing the tasks instead of repeating them. Okay, so we saw that we can train somebody quickly by using what is called synergy-based repetition of hand movements. So there's also a third application which I don't have time to go over, but we were saying that you can also devise biometrics, because these hand synergies, your hand synergies, are different from my hand synergies. So you can also do that. Okay, so that's the third application, but I'm not going to go through it. So in terms of future research, I'm looking at two major applications. One is motor control. I'm still looking at using techniques like transcranial magnetic stimulation to see if I can stimulate basal ganglia and cerebellum. We're trying to see if we can look at internal models in cerebellum. We're trying to see if we can use neural EEG control to control hand exoskeleton in real time. And we want to use a lot of deep learning methods to control this exoskeleton. And also, we're trying to see if these techniques can be used in motor control and motor learning. And we want to see if we can accelerate motor learning, that is to speed up motor learning using these synergy-based motor learning techniques. And we want to use virtual reality environments to devise, just like the virtual hands that you're seeing. And we want to see if we can use these algorithms in rehabilitation and rehabilitative exoskeletons. Okay, so I want to close with acknowledgements. These are outstanding undergraduate students and graduate students that worked in my lab. This is my lab at Stevens Institute of Technology. These are my, this is my PhD student. Let me see, this is my PhD student. And this is another PhD student. We also go out and eat at a lot of Indian restaurants here. And these are a lot of students that have worked in my lab. And in the backdrop from our university is New York skyline. And you'll see the new Freedom Tower, where there were twin towers previously. And these are all these types of research. It's not possible to do this type of research without expert mentoring. I've got a lot of help from a lot of mentors, my PhD advisors, my postdoctoral advisors. Here's a very famous scientist, Mike Boninger. And here is Pepe and Marco Santello, very famous scientists. And here is Doug Weber, my postdoctoral mentor. And here is a very famous neurologist from Hyderabad, Care Hospitals, Hyderabad. I collaborate with them a lot. You know, when you do this type of research, you need support, you need financial support. And I'm very, very grateful to National Science Foundation. And also, I'm not sure how many of you know this, United States, India, Science and Technology Endowment Fund also funded my research. And there are a lot of medical center collaborations. As you can see, this is very, very interdisciplinary research. You need medical centers, you need research labs, you need engineering. This is very, very interdisciplinary research. And thank you very much for this opportunity. And I'll take any questions and then I'll start my video. Then just so you guys know, this is my email address, ramana.vinjamuri@gmail.com. I'm actually recruiting PhD students. If you have some interesting students who are interested in my research, please send me an email and I'd be happy to share with you what are the opportunities that I have in my lab. Okay. Let me just. So I've stopped screen sharing, right?
Yeah, correct.
Okay, thank you. All right, so let me take any questions you have. Just going through the chat. Ooh, there's lengthy questions. Okay. Always good to see questions. Okay. Sir, you control the motions of the glove using the muscles of the left arm. Is it possible for all loads? Yes, that's a very good question. So, not possible for all loads, right? It is only able to carry up to certain weights. And our focus was mainly to be able to lift the objects that that we use in daily activities of daily living. Okay, so you may not be able to lift like a 50 pound or 50 kg rice bag with the exoskeleton. Okay, so you cannot carry heavy weights, but you can carry objects that you can use in regular daily activities. Okay, because the maximum load capable of being withstood by the sensors is far less than that of the arm. Oh, that's a very good question again. So as long as you have a firm grasp, you can lift heavy weights with your arm. So we made sure that the exoskeleton provides a firm grasp, and the firm grasp is provided by a lot of friction within the palm as well as the tightness of the grasp. So what is the largest possible load with the exoskeleton is designed to lift? So we go up to what we have tested is up to 20 pounds. I think we can go up to 20 pounds. Another general question: in COVID situation, there are various electronic gadgets in ICUs which need to be sanitized. So how is this accomplished? Because the ICU patients are far more riskier compared to the ordinary population. So that's again a very good question, but it's a very far-fetched question. I don't want to control any medical robotics yet with these technologies. There are already surgical robots like Da Vinci, for example, that can do medical robotics. But these are very, very interesting questions. Thank you so much. This is Shiva Shankaran. Okay, thank you.
Hello, sir.
Yes.
Can you hear me?
Yeah.
Yeah, I'm Karthik. So you mentioned about the synergies in the hand movements or joint movements in general, right?
Right.
So you're assuming that every joint is some kind of a actuator which can be controlled by a continuous signal from the brain, like a combination of signals for every joint.
Combination of joints. Yeah, I'm trying to control combinations of joints.
Yeah, so let's say there are 3 joints in 3 fingers. There is some particular combination, and then this has to be a 3-dimensional signal in specific with respect to time, but you're making it into a smaller dimension of signal.
Right. So so let's say I get so I put an EEG cap on you, and let's say I get 3 brain signals from you, 3 signals. Okay. And with those 3 signals, I'm controlling. With one signal, I'm controlling 3 joints of the thumb. With one signal, I'm controlling 3 joints of the index finger. And with the other signal, I'm controlling all the other 3 fingers. Because these other 3 fingers, they don't have much independence. Okay? So you can think of this as a puppet show. Okay? So you're pulling strings and you're making the puppets dance, right? So just like that, your 3 brain signals are pulling strings either on thumb or index finger or on the other 3 fingers. So if you're pulling the first 2 strings, you can make your 2 fingers go like that.
Yeah.
If you're pulling the other 2 signals, then you can make the other fingers go like that. If you're pulling the first and third, you can do this.
So the coefficients give us the amount of control on the joints, like how far they have to bend.
Correct. Mm-hmm.
And like, so there are these three actuators, like in a robotic hand, like you have these three actuators, which each is independently controlled with one signal from the brain. So there's a
Right. So
combination.
there are, okay, that's a good question. So there are 10 actuators within the exoskeleton. There are 10 actuators, but they are being controlled by only 3 signals.
Okay.
Okay. So the way the split works is the first 2 motors are controlling. So first of all, there are
15 joints in our hands, right? Like, to be precise, like, yeah.
Correct. There are 15 joints in the hand, but we're using only 10 joints for this purpose because these joints, they're called distal interphalangeal joints.
Okay.
These joints are not independent of these joints.
Okay. If they, yeah. Okay. Yeah.
So that's why we're kind of ignoring those joints, and we're just saying that let's stick to just 10 joints within the hand. Okay. So these 10 joints, the first 2 joints of the thumb are controlled by one signal. The next 2 joints of the index finger are controlled by another signal. But the next 6 motors are all controlled by one signal.
Okay.
Okay. So that's why we're using low dimensional control signals to control high dimensional end effectors.
Okay.
Thank you. Very, very good questions.
Just as an extension to this question.
Yes.
You have used 3 signals from the brain to control the 10 joints. But actually, for a human being, how many signals are used?
That's a very, very good question. So my working hypothesis is that if there are 10 joints, our working hypothesis is if your brain is intelligent, it will not use 10 signals.
Okay.
Right. That is the hypothesis. If your brain is intelligent, it will try to use as many less signals as possible to accomplish a very, very complex task. And how will it do that? How will it do that? Hopefully by using these synergies, right? If I can have a synergy that can control this whole hand, I will use that synergy once, right? Instead of going to each joint and telling move this a little bit, move this a little bit, move this a little bit. Instead of doing that 10 times, our hypothesis is that if the brain is intelligent, which we all think it is, right? Then it will use as less signals as possible to control as many joints as possible. That's a very good question. Thank you.
Thank you. Thank you.
I don't know if that's noise or I don't know if they're asking a question.
Yeah, not clear. Voice is not clear.
Not clear. Yeah.
Sir, hello.
Yes, Shaswini, I don't think
Hello?
I can.
Am I audible?
Yeah, now you are. Yeah.
Yes, sir. So basically, for hand, you have a controller, right, in the hexon, which you program and control. For that, we do need energy, right? So, are there any ways on building the hand energy efficiency, like using energy from some part of the body, like medical ways, that be somehow incorporated into this?
Yeah. So again, that's a very good question.
Like
So
any research related to that?
right. So right now the exoskeleton is powered by external power support, right? But if we were to harvest the energy from the body movements, can we do that? That's a very, very good question. There are a lot of ongoing research about this. One way to do that would be, well, so let me break this down. So these technologies are for people who have paralysis. Okay, so if they have paralysis, they're usually in wheelchairs, or they have assistants helping them. So there is some kind of carriers with them. If they have that kind of devices, then it is very, very easy to put batteries on these wheelchairs and power these devices externally. And these batteries are mostly rechargeable, so they're not expensive. So you can recharge them, reuse them, and power your devices. But what you're asking is if we can get the energy from a body power device, right? So you can also do that. You can also do that if they have movements. But the problem is that these individuals that we are addressing, they may not have movements. They may not have movements. But say, for example, soldiers, if soldiers were using these applications, then definitely when they're running, they can use their body movements to generate friction and generate energy, store it, and use that to drive exoskeleton. That's again a very nice question. I don't know if I answered that or not. Did I answer your question?
Yes.
Okay, thank you. And Gopinath, whether combinations of multiple finger patterns are possible. Yes, so that's exactly what we're trying to address through this synergies framework, that we can combine these movements in different weights. So I can start playing piano with my hand by pulling strings on these fingers differently. Okay, so it's definitely possible. We can do that using brain signals as well as muscle signals.
Anand?
Sir, thank you, sir. On behalf of IEI TLC, I thank you for your wonderful lecture presentation. Thank you, sir. Now I request our Honorary Joint Secretary N. Shivakumaran for giving formal vote of thanks. Sir, Shivakumaran, sir.
So good evening, everybody. First of all, I like to thank our friend. On behalf of IEI TLC, I like to thank Ramana Vinjamuri from Steve's Institute. So it was a very interesting talk, and we could see that we had a very good gathering of participants from IEI TLC and TNS state Tamil Nadu state chapter. So here I like to place my sincere thanks to all the past chairmen of IEA for their participation. And I like to, in spite of his busy schedule, I think Ramana has came forward to accept to deliver a very valuable lecture. And it is a kind of synergy, not only created a man-machine interface, it is also a human-machine interface. So usually we'll have MMI for many of the critical control applications. So the synergy is on human-machine interface. I think this is really a very important aspect of how these things are going to create the change in the revolutions of the scenario. So in this aspect, I also like to place my sincere thanks to our chairman, Kumaresan, secretary, for kindly permitting us to have this lecture, especially on a very important subject. I also like to place my sincere thanks to PA Karthik, Assistant Professor in IIT Trichy. We are all a team with Ramana. And as he said, we may expect, we may postpone the trip instead of August, we'll have in December. So Ramana is always invited to Trichy for everything. So we are very much happy to hear from you, Ramana. I also like to place my sincere thanks to, it's a very good gathering of participants from IEI as well as students of NIT Trichy. So we have very good gathering of students who really are in hands of biomedical instrumentation. We could see in spite of their examinations, classwork, everything, I could see students are very active, and their questions put forth by them are very good. I also like to place my sincere thanks to IEI TNSC for everything they made, especially on the Zoom connectivity. And this is a joint program with IEI TLC and IEI TNSC and CSI Tiruchirappalli. So I look forward to have more such lectures in future. So thank you all. Thank you, everyone.
Thank you, sir. Thank you, Ramana, sir.
Thank you.
Ramana.
Thank you all very much for this opportunity. It was great to be with you all. I wish I can have more personal interaction. Maybe very, very soon. I will come. I'll come there. And thanks to the student participation. Very, very grateful to you all. Thank you very much.
Thank you.
Thank you. Thank you.